Hello guys, so we are going to discuss on quantum physics and the topic which we are going to discuss is the concept of wave function. So we are aware that this universe is made up of matter and radiation. So when we talk about matter, the particle come in our mind. So we say that matter shows us the particle nature because every particle in this universe we consider them under the matter. And when we talk about radiation, radiation means light, the electromagnetic radiations. So electromagnetic radiation shows us the wave nature. But according to some phenomena which are observed in the earlier centuries, it is observed that matter can sometimes show the wave nature also, while the radiation can sometimes show the particle nature also. So this concept we write this concept under the dual personality means matter and radiation shows us the dual nature, that is particle nature as well as the wave nature, right? So here why we are considering the particle nature or a particle nature of radiation or wave nature of a particle. So guys, in quantum mechanics, as we know that we deal with the microscopic particles, right? We usually deal with the particles which are at atomic level or nuclear level. So at that time, in order to find the position of the particle, it is very uncertain. Okay, we cannot exactly find the position of the particle. So at that time, what we do is instead of finding the exact position of the particle, we go with the another concept, that is we go with the probability of finding the particle over a and over a particular volume or over an entire region. Okay, so this helps us to guess that where the particle should be present over a region. So if we are dealing in atom, so in an atom where this electron will be present, so we cannot find the exact position, but we can the probability of finding the particle over that region, over that volume. Okay, so finding the probability over a volume, say let's say dV be the volume. So probability of finding a particle over a volume dV, this quantity is directly proportional to the amplitude of a wave which is assigned to that particle, and it is nothing but the square of the amplitude. So this relation tells us that this probability is directly related to amplitude, which we can see that it's a property of a wave, right? So indirectly this tells us that in order to find the probability of the particle, we need particle to exhibit or to behave like a wave. So it should exhibit a wave nature. So therefore, in quantum mechanics, we consider the wave nature of matter and assign a wave function, that is psi, to a matter particle. Now, what is this psi? So this psi is assigned to a matter particle. So of course, this psi will give all necessary required information about the particle. So this psi is supposed to give all necessary information about the particle. Now what is this psi? How we are going to select it? So mathematically this psi is nothing but it's a complex function, and it is written as the function of position vectors of the particle which we are considering and the time. As I told you, it's a complex function. So this representation is a mathematical representation of a psi, which is the function of position vectors of the particle and the time coordinate as well. So these wave function for a particular particle, for a single particle, So this wave function for a single particle, it can be, means we can separate the variables for a single particle system. So for a single particle, we can separate the space coordinate and the time coordinate. So for single particle, this psi wave function, we can write it as psi of a particular particle. Let's say it's as a jth particle into e to the power minus I omega t, where omega represent 2 pi f, that is f is the frequency of wave, right? And I, we all are aware that it is under root of minus 1. So guys, here we have seen that how we have assigned a wave function which gives us all the necessary information regarding a particle which is assigned to, and how we can separate the wave function in a space and a time coordinate for a single particle. And further, I'll just like to tell you that if we are working in a time independent potential, that time we can neglect just time and we can just write psi as a function of space coordinate itself. And when we are working in time dependent potential, that time we can consider psi as a function of position as well as the time. So in general, we are going to talk about time dependent, and when we are going to consider the independent potentials, time independent potentials, that time we are going to just uh, skip this term including the time factor. Right. So now guys, here we have seen how necessary psi is in order to tell us, in order to give us the information about the particle. So it is very much important to select the wave function, to assign a wave function to a particle with certain conditions. So let's see the conditions for physically accepted and well-behaved realistic wave function. So the first condition tells us that this wave function should be finite, it should be single valued and continuous everywhere in the space. Second, this derivative, the derivative of psi with respect to time should be continuous everywhere, or it can be discontinuous under some conditions, like if the potential, as I was talking about the potential in the last slide also. So if the potential has this infinite discontinuities at some points, or if the potential under the particle is of a direct delta function, at that time this derivative can be discontinuity, no problem. That time we can also select this psi as a wave function. And the third important condition for this wave function is that it should be a squared integral. What is a squared integral? That the integration from 0 to infinity of square of dr should be a finite value. It should be a finite value. So guys, in order to grab the actual concept, let us see that one-dimensional picture of the wave function. So when we are going to deal with the one-dimensional wave function, here we are going to just select the x coordinate of the system and the next coordinate will be t. So for one dimensional, let us consider that our particle is moving in an x direction. So as it is moving in the x direction, it will have some momentum in that direction, that is px. And according to the de Broglie hypothesis, this particle will supposed to have the wavelength that we call it as de Broglie wavelength, and that is nothing but h upon px, right? And for such a particle, if you are going to write a wave function which is time independent, now here guys, we are working in a time independent potential. We are just considering the case so that the concept should be more clear to us. So for time independent potential, the wave function for such type of particle which is moving in an x direction having momentum px can be written as psi is equal to some psi of x. Okay, it will be just depending upon the coordinate, space coordinate, and mathematically we can express it as psi of x, that is a e to the power I k x. Now here this a will represent the amplitude of the wave, right? And this k is nothing but the angular wave number, which is having its direct relation with the wavelength. So as wavelength come into picture, our momentum and that comes into picture. So this is how we represent a wave function in one dimensional system. Okay, fine. So coming back to next topic, that is now means we are dealing with the wave function itself. So when we assign, so guys, when we assign a wave function psi of x to a particle, that is a is equal to e to the power I k x, and the things we have just listed down. So now this wave function, it tells about the position of the particle. So it will be again uncertain to find the wave function. What we will do by finding a wave function? What we are interested in, that we are interested to find the probability where the particle should be present. So probability that the particle should be present over region, small region dx, that we are going to write it as p dx, and that is equal to integration of psi square dx. Right? So suppose our particle is supposed to be present between this interval a is less than equal to b, means we are supposing that it's just like we are supposing that the electron is present over the radius of hydrogen and the nuclear size of the hydrogen. So this is the lower limit and upper limit where the electron should be present. Right. So in such a way, if a particle is present over a time interval over a position A and B, so for such a region, the probability of finding the particle in region A, B over a small interval dx is nothing but integration from A to B of this function's square into dx. Right. So now if I just draw a wave function like this, okay, and here now I assign a axis. Now here I'll draw an axis. So suppose this is my axis. So this is my origin, this will be my x-axis, and this will be my y-axis. Now we are only limiting our wave function to find to be over around the x-axis. So if suppose this is A point, this is B point, and the particle is supposed to be finding over here region. So square of this wave function, what it will give us? So it will give us the area under this. So this area under this curve, which I am shading right now, so what is this? So this area is nothing but the probability that the particle will be present between A and B. Right? So if we are going to increase our limit, increase our boundary, the probability will accordingly increase. right? And as we are all aware about that the value of probability lies between 0 and 1, right? So over the entire x-axis, if we consider entire x-axis, then over entire x-axis, the probability that the particle will be present over entire x-axis, that is, will be from minus infinity to plus infinity of psi square dx. Now here guys, we are considering the range from minus infinity to plus infinity. So over entire x-axis, there will be particle present, right? So this probability will have the maximum value that is equal to 1. So this condition means when the wave function satisfies this type of condition, then the wave function is said to be the normalized wave function. Normalized wave function. What is basically normalized? Normalized means it is a statement that yes, particle is present between minus infinity to plus infinity. So this gives us, it gives us a uh, kind of proof that yes, our wave function is valid for a particle which we are assigning. It is present between minus infinity to infinity. Now, by reducing the limit or by doing various repeated procedures, repeated examples, we are going to find some positions of a particle. Now here also, as I told you, that we are going to find certain position of a particle, right? As I told you, this minus infinity to infinity of psi square dx, this value is equal to 1. And the wave function satisfying this equation, we called it as normalized wave function. And this condition is the normalization condition. This is the normalization condition. Okay. So now, guys, when we look towards the normalization condition, we know that our particle is somewhere present between minus infinity to infinity. And by just reducing the limits, by finding the probability, we can just find where the particle should present over the region, right? So if we take number of number of values, and find the probability and take an average. So that time if we take the average of those values, so that will give us the average position of a particle. So this thing can be done mathematically using this wave function, that we can find the average value of a function. Suppose if we are here, we are finding the average value of position, right? So if you are finding the average value of position between say minus infinity to infinity, so that time we call such value in quantum mechanics, we call the average value of position as the expectation value of position, or expectation value of a quantity. Okay, here we are taking that quantity as position, and we represent it with this triangular bracket, and the quantity whose average we are going to find is written in between this parenthesis of this kind. And the mathematical formula for this is delta, this expectation value of x, and the integration goes from minus infinity to infinity, psi star x psi dx. Now guys, as I told you, psi is a complex function. So here, psi star is nothing but the complex conjugate of psi. Okay. So likewise, if you want to find the position, the expectation value for momentum in the x direction, that time we can write this as in this way. and it will go from minus infinity to infinity, psi star momentum psi dx. So this will give us the expectation value of momentum in the x direction. In the similar way, guys, for any function f of x, if you want to find the expectation value of that function, we just need to write this in between these two wave functions, that is psi star and psi, and just integrate over from minus infinity to infinity. So with the help of this, we can find the expectation value, and that is the average value of a function. Thank you, guys.